I want to quickly review the slides that I covered on Tuesday. I'm going to do this pretty fast just to remind you what the key takeaways were from each of the slides and make a few comments, so hopefully about the linear space version of finding the best alignment of a pair of sequences. Okay, so to get started, let me just remind everybody sort of what does designing programming using dynamic programming involves. You want to think about characterizing the solution to a problem in terms of solutions of smaller problems. The way that's typically done is you think about the objective function that you're trying to maximize or minimize and write down a recurrence relation that involves that objective function. And where the recurrence relation on the left-hand side is the expression for the larger problem, and on the right-hand side are the expressions that involve solutions to the smaller problem that are involved in making up the larger problem. I won't say too much about this slide. The point here is to try to, as you're trying to keep straight the different design paradigms, to make sure that you spend some time comparing and contrasting them so you understand how they're different and what that means in terms of what problems they might be applicable to. This slide just has some application areas for dynamic programming, and you'll be happy to know that dynamic programming is useful over a very broad range. This just scratches the surface of problem areas. Quick review. This slide is here for just as a quick review of knapsack to show you what I mean in terms of finding the optimal substructure and expressing it as a recurrence relation. So here at 0-1 knapsack, if you recall, it involves you've got n items, and each item is characterized by its value and its weight, and you want to see what the most valuable set of items that will fit in a knapsack of capacity C. So the first step is always to write down the function that's going to represent the optimal solution in the recurrence relation, and that will almost always be the objective function, the function you're trying to maximize or minimize. So in this case, it's going to be opt. N represents the number of items that we've considered up to this point. It's sort of the set of items that we can choose from, and C represents the current capacity of the knapsack. So if we think of the thief being, he's going to consider the best he can do out of n items with C capacity, well, what that problem either has, that solution either has the nth item in it or it doesn't have the nth item in it. If it doesn't have the nth item in it, then clearly it would have to be the optimal solution for just n minus one items up to in a knapsack of capacity C. If it does, then it would be the value of the knapsack with n minus one of using n minus one items as its consideration set with a knapsack of capacity C minus W of n. That's the weight of the nth item, so there's less room in the knapsack, plus the value of item n because that's now included in the knapsack. As mentioned earlier, there are lots of applications. The really important thing on this slide is that a lot of the algorithms for string similarity and sequence alignment use different terminology, and that's because they were developed independently in the different fields. And here's a couple of examples: Levenstein and Needleman-Wunsch. And what characterizes the differences are usually the parameters that go into the string similarity or edit distance function, the gap penalty and the mismatch penalty. And the mismatch penalty can even depend on what's being mismatched in extreme cases in bioinformatics. So hopefully this slide is old hat to everybody. I mean, we're going to look at this from a string alignment comparison to initially. And so we've got two sequences, X and Y, and what's an alignment? Well, an alignment actually like the word matching a little bit better, although it confuses it with other areas of computer science. But the idea is you match up the elements from one sequence to another sequence, and you have to do it in the order in which they appear in the original sequence. So, and that's what means that you're not going to allow them to cross. So I won't go into detail on that, but you can basically see it down here. This gives you an example here of where in X, there's a character and it's aligned with a gap. Here's a mismatch, and here you've got a character in Y and it's aligned with a gap, and the others are aligned together. So for these matches, typically you might get some positive number. So I won't spend any more time on this because I think most of you are pretty familiar with this problem. So what's the optimal substructure of this problem? Okay, so this, depending on the gap penalties and the value of a match versus a mismatch, etc., you can either be trying to minimize the cost, say in an edit distance characterization of the problem, or you might be trying to maximize the similarity. But in either case, what you basically have to do is think about what the sort of happened in the very last stage of the optimal solution. And so one possibility is that the symbol from the X sequence is matched with the symbol from the Y sequence, in which case, right, you get the score for that matching. And that can either be positive or negative, depending on whether it's an actual match, whether they are the same or whether they're different. The other possibilities are the last character in the X sequence gets matched with a gap, okay? And then what you get is the score for that plus whatever the optimal value is for the sequence for X up through I minus 1 and the sequence for Y up through from 1 to J. And very similarly, if the last character from the Y sequence is matched to a gap, then you get that score and then the minimum cost or the maximum similarity for the X sequence all the way up through I and the Y sequence up through J minus 1. So one way to view all this is you can think of it as a graph. And that's what we'll do here just because it's going to make the dealing with the problem and trying to reduce the amount of space required to be linear as opposed to quadratic. So here's the graph. And so you can think of the Y sequence as being the columns and the X sequence as being the rows. And the goal in terms of creating the alignment is to move from this corner, upper left-hand corner, to the lower right-hand corner. And each alignment was going to correspond to a unique path. So this just illustrates the scoring matrix given these different values. +1 for a match, a mismatch is 0, and a gap is -1. So you can see here, up in the upper left-hand corner, you're going to start out, and the options are basically either to assign a gap to G, in which case you get -1, because that's what you get for a gap, or you could assign a gap to A by moving down here, and that would also be -1. Or you can just mismatch those two characters, G and A, in which case you get 0, because that's the value for a mismatch. And you just continue to fill on the table that way all across the board. I should make one comment, of course. The base case is this row and this column, and it's where the characters are matched with spaces. So as you can see, since the penalty for a space is -1, you get that set of decreasing numbers, and same thing down the first column. Once you've got the matrix filled in, which is illustrated here by filling in the vertices in the graph, you can then trace back and figure out where each value came from and use that to figure out what the alignment is. So for instance here, when we have this diagonal element, the 1 here came from the 0 here because there's a match between the C's. Since there's a match between the C's, okay, you came back here. Now, once you're back here, there's two possible ways you could have gotten here. You either could have gotten here by the mismatch between A and G, this A and this G, okay, that would be this line, or you could have come from over here by inserting a gap for this A. So that the first thing I talked about there, that corresponds to this column right here in this alignment, and the second situation corresponds to this column in this alignment. And similarly, you just do things to work your way all the way back up and get these two possible alignments. If you're at all unclear on this, I suggest you just work your way all the way back and see how you get these two alignments to make sure you understand how the traceback works. So with this implementation that I've just been talking about, basically what you end up is the time is quadratic. In other words, it's the product of the lengths of the two sequences, and the space required is also the product of the length of the two sequences. Now, what we'd like to be able to do, especially for problems where there are really long sequences like bioinformatics, is we'd like to be able to reduce the amount of space that's required. And so what we'd like to be able to do, in fact, is get it down to be linear space, and that's going to be possible. Now, you can do this. This part is pretty straightforward in terms of computing the optimal value, because all you do is, Jen, I'll illustrate this in the next slide. You just use basically two columns, and you use one column for the previous values, and then use that column to compute the next column. And exchanging, and you could do it with rows too, and exchanging either the columns or the rows to the first one, or one of them always contains the previous column, and then the other one contains the next column that's being computed. Hirschberg came up with a very clever combination of divide and conquer and dynamic programming that reduces the amount of space required to actually get the alignment. See, up here you can't get the alignment. To actually get the alignment without using quadratic amount of space. So this is just a quick graph I added to illustrate a little better, at least conceptually, what's going on in terms of being able to only use linear space and computing the values. So you start out and you have, this is the base case right here. You can think of that as the base case. And you use that to compute this column, right? Obviously you can do that because what you need to compute any node is the value above, the value diagonally to the left, and the value directly to the left. And so as long as you fill in this column going down, you're going to be okay. And then what do? You move, you can think of the window as moving over, and then you use these new values to now compute this next one. So you can have this, think of this sliding window, and it's basically moving across the entire graph. So how do we find the actual alignment? So this is pretty clever. What you notice is, let's take a typical problem here. We're going to divide the matrix in the graph, the directed graph. We're going to divide it right down the middle, just like you typically do in divide and conquer. And we're going to notice that if this were the optimal alignment shown here, that this number here actually has to reflect the cost, the optimal cost you can get to go from this corner to this particular value. And there's symmetry here, because in fact, if you take the remainder of the graph that goes from this spot ij in the complete rectangle, that it also, this part of the path that goes back to this corner also has to be the optimal path, but now it's the optimal path between this corner and this position. So if you think about it, there's an optimal substructure here. Namely, if this node is included in the solution, then the path from the upper left-hand corner to this node must be the part of the optimal path, and the path from this node back to the lower right-hand corner must be part of the optimal path. So in other words, you can split the optimal path from the upper left to the lower right. You can split it at this particular cell, and it's the cell that's on the optimal path. The question is, how do we find that cell? Well, if we're trying to minimize the edit distance, for instance, we find that by computing the optimal paths, the value of the optimal paths, from the upper left-hand corner to all these slots along the n over 2th column. And we also compute the optimal values going from the lower right-hand corner to all the cells along this column. And then what do we know? Well, we know that the optimal path from the upper left to the lower right will minimize the sum of the lengths of this path with this path. But we've already computed f, which is the value for all the paths from the upper left to this column, and g, which is the value of the optimal paths going from the lower right-hand corner to all the cells in this column. So all we do then is we know that the optimal path is going to be the sum of those two function values, and in fact it's going to be the cell that's going to be on the optimal path is the one that minimizes those two. Finally, once we've got that cell, then now we're ready to do the actual conquer part. So this gives us the division, and then what do? We need to find the path now between here and the upper left-hand corner, and we can do that by just looking at this little rectangle here and splitting it down the middle. So maybe potentially using that as the split. Okay, and similarly on the right-hand side, we use the rectangle over here and split this, and then find maybe it's this column, and find that we go here, and then there's some optimal path. And the next one as we do the next recursion down. Now, what's a little tricky here is understanding how you're actually going to, once you find all those cells, how you have to create the path. So the next slide I've drawn will try to give you a little help in visualizing what's going on. So in this picture, I've tried to leave out a lot of the detail to try to make it a little clearer what's understanding, how you can understand what's going on. Here's our original split. Now what will happen is then we'll call it recursively on this side, if you remember over here. And so we'll get a split here. And then we'll have two pieces we'll have to consider. We're going to have to consider the piece over here and the piece over here. So I'm just going to keep going to the left. And so now we'll focus on this rectangle and we'll split it in half. Now my picture is not very good. You got to think of this as being in the middle, and etc. So you'll get all these as you do the recursion all the way down. You'll get all the different cells for each column. Now what makes this a little bit tricky, remember, is some of the moves are going to be, there's going to be two cells. And so you do need in one column. So you do need to be a little bit careful once things get narrowed down in terms of what insertions where you have to make the insertion, whether say above one cell in the column to the right, or maybe below the other cell in the column on the left. But I'm not going to worry too much about that right now. You might give that some thought. It's actually, the time I did it, I actually felt a great satisfaction once I'd figured out a good way to do that. Finally, I talked about this in class. We want to actually show that the running time hasn't gotten any worse. I mean, in terms of asymptotically. I mean, it's pretty clear that there's going to be more overhead. The constant term is going to be bigger. But it's still quadratic in the lengths of the sequences. And without going into too much detail, if we use this again, I'll go over in another context, I'll go over it again, so don't worry about remembering too much right now. But the idea is pretty clever. You have to do induction on two parameters, and that's a standard thing to be able to do in mathematics. And because our objective function here, our recurrence relation, I'm sorry, I shouldn't have said objective. The recurrence relation for the running time involves two parameters. So the way you can do this is, well, let's write down the recurrence relation and not worry about how we're going to solve it to start with. And we find it's something like this, where we split down the middle, n over 2, and the left-hand side is going to go from 0 to q, and the right-hand side is going to go from the number of rows minus q to n minus 2. And then there's going to be some overhead. Now, the overhead, if you think about it, is going to be some constant times mn. In other words, the size of the matrix, right? Because that's how you find the cell. You do the sequence alignment or the edit distance over the entire matrix, and we know that that's quadratic. So this term is going to be quadratic. And these two terms, of course, come from these guys. So the next step is to make this sort of assumption that we're going to choose this constant. So this constant alpha, it can't be arbitrary, but we're going to choose the constant so that the time for the base cases of m and n is going to be less than or equal to 2 times c to the m times n. And then we just use that and we just go and we say, well, okay, if that formula works for the first term in the recurrence relation and it works for the second term in the recurrence relation, and we've got the third term in the recurrence relation, that doesn't change, well, then we're going to still get the same inequality. And this portion of the slide is just pure algebra. You know, you learned it in freshman year of high school. So you're just manipulating the symbols, and if you start out assuming that the base cases are computational complexity, time complexity is 2 times cm, then you end up that for any of the inductive case, it remains to be 2 cm. So I hope that's helpful, and please don't hesitate to ask questions. I know I went through that pretty fast, but I did take the time to tune up the slides, and I thought that hopefully this is helpful enough that if you do have questions, it'll make it easier to frame any questions you might have or confusions.